Hello everybody, this is John Whitaker for the Probability Graduate Level class, and this is going to be our sixth video lecture, and I want to continue talking about some specific discrete random variables. We'll just cover two today, along with examples of them and characteristics such as what their PMFs are, their expected value, and their variance. Okay, let's go ahead and get started by defining the the Poisson random variable. So as a definition, a Poisson random variable we'll call it X, is a discrete random variable whose probability mass function is m of x, and it's equal to e to the minus lambda, lambda to the x, all over x factorial, where lambda is some fixed number just greater than 0, and x is equal to 0, or 1, or 2, and it goes up forever. In this case, we say x is Poisson with parameter lambda. All right. Well, one of the things we want to make sure of is that if I can sum up the PMF of Poisson over all of its output values, that I get 1. And a fact that helps us get that is Taylor's theorem. Now, I'm not going to write up Taylor's theorem formally. I'm just going to remind you of the Taylor's theorem formula. So here's the Taylor's theorem formula. And what it says is that if a function has a power series representation, what it looks like the sum is n runs from 0 to infinity of the nth derivative evaluated at some number a over n factorial. So that's a number, and then it's times x minus a raised to the n. Now, as a fact, or in particular, turns out that e to the x does have a power series representation. And what it looks like is the sum as n runs from 0 to infinity of x to the n over n factorial. Okay? And here in this particular representation for the function e to the x, we're having the a value be equal to 0. So that's what we get. All right. So note, when we look at the, if x is Poisson with parameter lambda, then the sum as x runs from 0 to infinity of f of x, well, that's equal to the sum as x runs from 0 to infinity f of x, let's see, that was e to the minus lambda, lambda to the x, all over x factorial. You pull out the e to the minus lambda, because it's a constant with respect to index x. Sum, as x runs from 0 to infinity, of lambda to the x over x factorial. And if we look at this part right here, it matches identically this sum that's right above, where the only difference is, in terms of its representation, is that here we had the index being n, but here we have the index being x, but they're identical. And that this x is being, the role of this x is being played by lambda. So the answer is e to the, well, it's supposed to be x, but x is lambda in this case. So we get e to the minus lambda, e to the lambda, and of course that is 1. So it's e to the 0, which is 1. So the sum of the PMF over all output values does equal to 1 for a Poisson random variable. Okay, next we want to look at the expected value of Poisson. So as a fact, if x is a Poisson random variable, with parameter lambda, then the expected value of x is equal to lambda. Let us prove that. Okay. So let's let x be Poisson with parameter lambda. Then, the expected value of x, by definition, is the sum over the x values of x times f of x. So the x values are from 0 to infinity. And that will be equal to the sum, as x runs from 0 to infinity, of x times f of x. Well, its representation is e to the minus lambda, lambda to the x, all over x factorial. And one of the things that's obvious is when x is 0, 0 times something is just 0. And so you might as well have the sum running from 1 to infinity of x e to the minus lambda, lambda to the x, all over x factorial. Now, e to the minus lambda is something that doesn't depend on x, so I'm going to pull that out. Sum, and here, this x and that, one of the x's, the x that is a factor in x factorial will cancel. And so I have the sum of x runs from 1 to infinity. Here this will be lambda to the x. And then this would be x minus 1 factorial. Well, we pull out a lambda too. And the reason that I think about pulling out a lambda as well is so that I have lambda raised to the x minus 1, and that will resemble Taylor's representation for the exponential function. So that's what we're going to do. Okay, so this is equal to e to the minus lambda, lambda, and then this is the sum as x runs from 1 to infinity of lambda to the x minus 1 over x minus 1 factorial. If we let y be equal to x minus 1 to kind of change the indice, we still get the same quantity, it just looks different. So e to the minus lambda times lambda, this will be the sum. Now y runs from 1 less than x, so y would run from 0 to infinity. This would be lambda to the y over y factorial. And that fits the exact representation for e to the lambda in terms of Taylor's theorem. And of course, e to the minus lambda times e to the lambda cancel from each other, we just get lambda. And that's the proof. All right. Well, as additional fact, if x is a Poisson random variable, and with parameter lambda, then the variance of x is also lambda. Okay. So we'd like to prove that. So here's the proof. We're going to let x be Poisson with parameter lambda. Note, we've got a formula for the variance, and that the variance for any discrete random variable is equal to the expected value of x squared minus the expected value of x to d squared okay. So the expected value of x, we've just found that that was lambda, so this part's going to be lambda squared. What's the expected value of x squared? Well, I don't know. So let's start calculating that. So the expected value of x squared is the expected value of a function of the random variable x. So it's the sum as x runs from 0 to infinity of x squared times f of x, which is equal to the sum as x runs from 0 to infinity of x squared times e to the minus lambda, lambda to the x all over x factorial. Again, when x is 0, the first term in this sum is going to be 0. So might as well start the sum running from 1 to infinity of x squared e to the minus lambda, lambda to the x over x factorial. Here I am going to take out an e to the minus lambda. I am also going to cancel one of these x's here with the x in the factorial. One, infinity. Here I have x, e, be just lambda to the x over, this will be x minus 1 factorial. All right, let's put out a lambda as well, because then the index, the exponent here will match that. So this will be equal to e to the minus lambda, lambda, sum, x runs from 1 to infinity. This will be x, lambda to the x minus 1 over x minus 1 factorial. All right, now let's again make a change in terms of the index. So let's let y equal to x minus 1. So that means that x will be equal to y plus 1. When I do that, here's what we'll get. That's equal to e to the minus lambda, and there's lambda, that's the sum. The x values ran from 1 to infinity, so the y values run from 1 less than that, that's 0 to infinity. it said x, but x is the same thing as y plus 1. And then it was lambda to the x minus 1. That makes lambda to the y. And it was over x minus 1 factorial. That's just y factorial. So we can break this up. It's the same thing as e to minus lambda times lambda. Here, this is, well, it's the sum, as y runs from 0 to infinity. I guess we'll take it out. Y, lambda to y over y factorial plus lambda y over y factorial. That's equal to, so here's e to the minus lambda times lambda. We break this up into two sums. The sum of y runs from 0 to infinity. Y lambda to the y over y factorial. And I'll distribute this. And then this will be e, so plus e to the minus lambda, lambda, and then here will be another sum, is y runs from 0 to infinity, of lambda to the y over y factorial. Okay. If you pull in the e to the minus lambda here, you'd have lambda times the sum as y runs from 0 to infinity, e to the minus lambda, there's a y I'll put in front, lambda to the y all over y factorial. Here we have plus. I'm going to leave this as is and note that this sum is nothing more than by Taylor's theorem. Remember this y factorial. That's e to the plus lambda. So it's e to the minus lambda, lambda, e to the plus lambda. Now this first sum that we have involved, this e to the minus lambda, lambda to y, y factorial, as y runs from 0 to infinity, that part right there is nothing more than the PMF of a Poisson random variable with parameter lambda. That's what that is. So as you sum it up as y runs from 0 to infinity, the index, and you times it by y, that's nothing more than the expected value of a Poisson random variable with parameter lambda. Well, we just calculated that a few minutes ago. That is lambda. So this ends up being lambda's there, and the sum is lambda. And here, this is plus lambda, which equals to lambda squared plus lambda. That's what the expected value of x squared is. So, the variance of x, that's equal to the expected value of x squared minus the expected value of x to b squared, which is equal to, this was lambda squared plus lambda minus the expected value of x was lambda, we squared, we get lambda squared, and lo and behold, the lambda squared minus lambda squared nothing, we just left with lambda, and that's what we were expecting. That's what the fact was that we were trying to show. Let's look at an example. Okay. Let x count the number of typos of a book. Number of typos on the pages of a book. Suppose x is Poisson with parameter lambda equal to 1. Find the probability that a particular page has at least one typo. Okay, the way I'm going to do this problem is that I'm going to say probability, so here's my solution. Probability that a particular page has at least one typo. That's equal to 1 minus the probability that the page has, well, I'm writing down the complement here, and the complement of at least one typo is no typos. Okay, so this is equal to 1 minus, well, the probability that the page has no typos would be f of 0, which is for the PMF, the value of 0. And so this is 1 minus, it would be e to the minus lambda, well that's minus 1, lambda, which is 1, to the x, which is 0, all over 0 factorial. Remember, the 0 factorial is 1. 1 to the 0, we're finding that to be 1. And so here I get 1 minus e to the minus 1, and I think that's about 0.63. There's about 63% chance that there's a typo, at least one typo on the page. Okay, as a comment, a Poisson random variable can be used to approximate a binomial random variable when, so a binomial random variable has parameters n and p. So when n is big and p is small. Remember, p is the chance of success occurring on each independent trial for the binomial random variable. And so p is small and n is big, you did a bunch of trials, then you can use your Poisson to approximate the binomial. And I'm going to show you why. Okay, so so this is the sketch of proof kind of idea. It's not have a good details to it, but anyway, we're going to let x be binomial with parameters n and p. Then, the PMF of x is, so let's remember for binomial, f of x is n choose x is what it was. Let's see. It was p to the x and then 1 minus p to the n minus x. And let's expand this a little bit, which equals, well, what is this? It's n factorial over n minus x factorial over x factorial. Here's p to the x, and then this is 1 minus p to the n minus x. Let's kind of work with this n factorial and n minus x factorial a little bit. Make a different representation, simplifying that fraction. So this is going to be equal to, it's going to be n minus x plus 1 factorial, that's what's going to be left in the top, over x factorial, p to the x times 1 minus p to the n minus x. Okay. Now let's make a substitution here. Let's let lambda be equal to n times p, and thus p is equal to lambda over n. So the PMF for this binomial, making this substitution. So here I'm going to leave this as is. And I didn't do this great. This is wrong. Oh, what a mistake. Let me change this. Oh. We had n factorial over n minus x factorial. What that's going to leave is the n times the n minus 1 times n minus 2, all the way down to the n minus the quantity x plus 1. I don't know what I was thinking. All over the x factorial. Here's p to the x. Here's it was 1 minus p to the n minus x. I'm sorry about that. That's what it should have been. So here, I'm going to leave this part the same. So n and n minus 1, n minus 2, all the way to be multiplied by n minus x plus 1. Over the x factorial. And then the p, we're going to say, is lambda over n raised to the x. And here, this is going to be 1 minus p raised, well, it's 1 minus lambda over n raised to the n minus x. That's what we'll do. All right, we'll reorganize some things here. This is equal to, so n times n minus 1 times n minus 2, all the way up to n. And I'm going to rewrite this. It's going to be n minus the quantity x minus 1. That'll kind of help me count. Look, this would be lambda to the x over n to the x. I'm going to move the n to the x over this guy. Okay. I'm going to rewrite this as lambda to the x over x factorial, because that looks like part of the PMF of the Poisson. So I'm trying to make the binomials PMF look like the Poisson PMF in some sense. And here I'm going to rewrite this as 1 minus lambda over n raised to the n, all over 1 minus lambda over n raised to the x. So that's where we are. What I'm going to do is I'm going to look at parts here of this PMF. I'm going to look at this part of the PMF and take the limits n goes to infinity and see what happens. I'm going to take the limits n goes to infinity of this top part of this fraction and see what we get. And then we're going to think of L over n as p, and we're going to think of it as p small, and when we take that from 1 and raise it to x, see what that goes to. This guy we're going to leave the same. Okay? And one thing, when I first look at this, that I want to point out to you, is that if you look at the number of terms in the top, number of factors in the top part of this fraction, here's 1, 2, 3, I don't know how many there are. Well, let's see what's being subtracted from n. Look, if I just look at the part to the left here, I've got two factors, n and n minus 1. And look what's being subtracted from n. It's 1, but yet I've got two factors. So it's 1 more than what's being subtracted from n. So if I look here, how many terms do I have to the left and the top? I've got 3, and that's 1 more than what's being subtracted from n. Here, when I say how many factors are in the top, it's going to be 1 more than what's being subtracted from n here. That's x minus 1 plus 1. So there are x terms, x factors in the top. And there are x number of n's in the bottom. Okay? So in that type of reasoning, what you can show is the following. So note the limit as n goes to infinity of n minus 1, n minus 2, all the way down to n minus the quantity x minus 1, okay, all over n to the x. Okay. This is like n over n is one of the factors, and the limit of that is n goes to infinity. You use Lopez rule if you want. You just get 1. When you look at n minus 1 over one of the n's here, and take the limit as n goes to infinity, that's going to be equal to 1. So each factor over one of the n's down here, and they have the same number of factors in the top and the bottom, when you take that limit, you just get 1. And so here, if you say that the limit of a product is product of the limit, which is true fact, you just get 1. So to kind of understand this, so when n is big, then this quantity, n times n minus 1 times n minus 2, all the way down to quantity n minus the quantity x minus 1, that's just a number here, over n to the x, that's going to be equal to, that it is approximately all right. Okay. Note, so another thing to observe that's part of the PMF of the binomial, the way we wrote it, was that if we have 1, I think it was minus lambda to the n, oops, let's say the limit, as n goes to infinity of this part of the PMF, the binomial, 1 minus lambda over n raised to the n, you can put this in a L'Hopital rule form, and what you'll find is it goes to e to the, I think it's minus lambda. That's what it goes to. All right. So when n is large, 1 minus lambda over n raised to n is approximately e to the minus lambda. Now, next thing I want to look at is when p is small. So note, the other part that is involved that we want to look at in the PMF of the binomial is 1 minus lambda over n raised to x. That was the bottom part, the denominator, that last fraction we had involved. This is equal to 1 minus, remember this is the same thing as p, raised to x. And when p is really small, this is approximately, okay, when p is really small, 1 minus something really small is like 1 to the x, which equals to 1 when p is very small. So let's combine all of this. Okay. So when n is big and p is small, the PML of a binomial random variable x is f of x, and the way that we've written it before, it was n times n minus 1 times all the way down to n minus the quantity x minus 1 over n to the x. This was was lambda to the x over x factorial. And we had 1 minus lambda over n raised to n over 1 minus lambda over n raised to x, which is approximately, this was 1, here's that lambda of x over x factorial, here this is e to the minus lambda, the top part, over, and the bottom was approximately 1, which equals to e to the minus lambda, lambda to the x over x factorial, which is the PML. Of a Poisson random variable. And that's what we're trying to show. Well, that's maybe more than the sketch of the proof. Well, let's do an example. We've done an example of Poisson, so let's move on to the next type of discrete random variable that I want to talk about during this lecture, and that's geometric. Definition. So suppose a Bernoulli experiment is performed independent times, independently, until the first success occurs. Where the probability of success on a trial, on these, anytime you do these things, is represented by a little p. Let x count the number of trials needed. Number of trials that occur. So x counts the number of trials that you need to do until you get the first success. Then x is called a geometric random variable. With parameter p. Let's talk about the characteristics of the geometric random We're thinking here P is non-zero. And P is non-zero, we're thinking that. Okay, note the PMF, probability mass function, of a geometric random variable with parameter P is, so it's f of x. Remember, this is the probability that it takes x number of times doing the experiment to get the first success. Well, here's what I think. What we know is that the last time we did the experiment, it was a success. What's the chance of that happening? It's big. The previous times we did the experiment were failed. What's the chances of each one of those previous ones being failed? Was 1 minus p raised to the x minus 1 for the number of trials that we did it previously. So we're multiplying those things together because they're independent. And so that's the PMF, where x can be equal to, well, x is the number of times we had to do the trial to get it. Well, it could have been the first success. So, it could have been 1, 2, 3. Well, it goes on forever. All right. Let's note the sum. If x, let's just say the sum as x runs from 1 to infinity of p times 1 minus p to the x minus 1. Okay, well, we're summing up the PMF overall, its output values, and we know what the answer should be. Let's make sure. The answer should be 1, let's make sure. So what I'm going to do is factor out p because it doesn't depend on x. And the name of this type of random variable is a geometric. And the reason it is because this sum is a geometric series. And if, in a geometric series, which we're looking at as a constant one, times something we call r, raised to a power, which depends on the index. And here, when you're in that situation, this will converge, this series will converge, provided that this r is between minus 1 and 1, and can't be 1 or minus 1. And if p is greater than 0, then this occurs, so we know that this series converges. And when it converges to, it's the first term of the series. So the first term of the series is when x is equal to 1. This will be the 0th power, that's just 1, over 1 minus the ratio, which is 1 minus p. So this is a calculus fact, something that's covered in analysis too as well. And so here this is a p times 1 over, well, 1 minus 1 is just 0, minus p is p, and of course you get 1. That's what we thought. Okay. Well, next thing I want to do is tell you the fact if x is geometric with parameter p, then the expected value of x turns out it's 1 over p. Okay, let's prove this. So we're going to let x be geometric. With parameter p. Okay. Then the expected value of x, talk about a discrete random variable, so we're talking about the sum over all x value 5 plus 1 to infinity. Here it's going to be x times f of x, which is the sum, x runs from 1 to infinity, of x times p times 1 minus p, okay, to the x minus 1. I can pull out p, and I will. And so symbolically, I've got a sum as x runs from 1 to infinity of x times 1 minus p raised to x minus 1. And so what I'm going to do is I'm going to let q be equal to, just for symbolic reasons, 1 minus p. Okay. Now, what we'll have is, so expected value of x is going to be p times sum as x runs from 1 to infinity. Here, we're going to have x times q raised to the x minus 1. Now, we think of q as a variable, just symbolically thinking of this variable. This looks like the derivative of a variable raised to a power, where we think of the power instead of being a variable, we think of it as a constant. So if you want, you can say symbolically this is p as x runs from 1 to infinity of the derivative with respect to q of the quantity q raised to the x. Now it turns out that you can pull this derivative, this limit, outside that sum. And so here we would have q to the x. And now we can think of this as a geometric series and say, well, that's p times the derivative with respect to q. And this is a geometric series, and its sum is going to converge to q over 1 minus q for a geometric series. So the first term over 1 minus the ratio. And so now I'm going to take the derivative of this. So this is symbolic proof here. This is p. The derivative, we use quotient rule, so it's right down the bottom, so 1 minus q times the derivative of the top with respect to q, that's just 1, minus, right down the top, there's q, times the derivative of the bottom, that is minus 1, all over the bottom to be squared. Okay, so that's p times, well, this is plus q, there's a minus q, so you just get 1 over 1 minus q to b squared. Well, what was 1 minus q? Well, that's p times 1 over 1 minus, q was 1 minus p, so that's 1 minus p to b squared. That leaves p over 1 over p squared, and that's 1 over p. And so symbolically, we got the result we were looking for. Wonderful. Next, we want to take a look at the variance. Well, it's a fact, if x is geometric, with parameter p, then the variance of x is equal to 1 minus p over p squared. We won't prove this. So we're going to let x be geometric with parameter p. Then, as we know by formula, the variance of x is equal to the expected value of x squared minus the expected value of x to b squared. I already got that. That's 1 over p. Note, the expected value of x squared, let's work on that. That's the sum as x runs from 1 to infinity. This will be x squared times p times 1 minus p to the x minus 1. All right. Now what we're going to do is we're going to skillfully rewrite x. So what I'm going to say is this is the sum. Sum as x runs from 1 to infinity. Instead of x, I'll write down x plus 1 minus 1. And that guy's got to be squared. Times p times 1 minus p to the x minus 1. Okay. When we multiply that out, that's equal to sum as x runs from 1 to infinity. It would be x plus 1 b squared plus 2 times the quantity of x plus 1. And it could be minus. Let me think here. Minus 1. You know what? I didn't write the way I wanted to. I wasn't paying enough attention. Let's go back. Some notes. Go back, make the correction. Instead of writing it this way, let's write it as x minus 1 plus 1. So x minus 1 plus 1 is still x b squared. That's going to change this up here. Make that change. That's what Michael Jackson would tell us. Make that change. Okay. So here, this will be x minus 1 squared. This will be 2 times x minus 1 plus 20 times 1. And then plus would be 1 to be squared would just be 1. And then times p times 1 minus p to the x minus 1. All right, we can multiply or distribute this p times 1 minus p to the x minus 1, split it up into 3 sums, and that's what we'll do all at one time. This is the sum of x runs from 1 to infinity. X minus 1 squared times p times 1 minus p raised to x minus 1 plus sum x runs from 1 to infinity of 2 times x minus 1 times p times 1 minus p raised to x minus 1. And then plus the sum as x runs from 1 to infinity of p times 1 minus p to the x minus 1. That's what we're on. This is equal to, so I'm just going to write this down again as is. So this is the sum as x runs from 1 to infinity of x minus 1 to b squared p times 1 minus p to the x minus 1 plus, here's the sum. You can pull out the 2, and I have x minus 1. Of course, x runs from 1 to infinity. P times 1 minus p to the x minus 1. But that last sum, that's the sum of the PMF or geometric. And we know it sums up to 1, so I'm just going to put plus 1. And now I'm going to let y equal to x minus 1. Okay. So I'll clear both of these first two sums. All right. Now, when we let y equal x minus 1, we get a sum as y runs from 0 to infinity. This will be y squared times p times 1 minus p to the y. Oh, this is outstanding. Plus 2 times the sum as y runs from 1 to infinity. This again will be y times p times 1 minus p raised to the y. And then this will be just plus 1. Now, what I'm going to do is I'm going to take out a 1 minus p. So this is equal to 1 minus p times the sum as y runs from 0 to infinity of y squared times p times 1 minus p to the y minus 1 plus 2. Again, I'm going to take out y minus p. This is the sum as y runs, it was from 0 here, runs from 0 to infinity of p times 1 minus p raised to y minus 1, and then plus 1. Okay, when y is 0, it doesn't contribute anything. So this is 1 minus p, sum, y runs from 1 to infinity of y squared, p times 1 minus p raised to y minus 1, plus 2 times 1 minus p, that's the sum as y runs from 1 to infinity. There was a y here that I didn't write down. Put that y in there. Y times p, 1 minus p, y minus 1, plus 1. I say y, just tell them it's human nature. That's what Michael Jackson does. Anyway, it's supposed to be y there. I'm stopping at the Michael Jackson. Here's what I want you to notice. Remember, we're going to let, I guess I'll make it on. Let x be equal to y. So this is equal to 1 minus p sum over the x's running from 1 to infinity x squared. P times 1 minus p to the x minus 1 plus 2 times 1 minus p sum, 6 runs from 1 to infinity, of x times p times 1 minus p raised to x minus 1 plus 1. The only reason I did that was just to give you a more familiar representation book. Here's what I see. This right here is nothing more than the PMF of a geometric random variable. And you're summing it over x squared times it. Well, that's the expected value of x squared. So that's great. Here, this is nothing more than the expected value of x, where x is a geometric with parameter p. And you got plus 1. So having made those observations, here's what we get. So, the expected value of x squared is really equal to 1 minus p times the expected value of x squared. Then plus 2 times, I think it was 1 minus p times the expected value of x, which is just 1 over p, and plus 1. So, if I subtract that, I have the expected value of x squared minus 1 minus p times the expected value of x squared equals to 2 times 1 minus p, come on, over p plus 1. And then here you factor out expected value, yeah, times, here's 1 minus 1, it's just p. Yeah, it's just p. All right. So this is equal to 2 times 1 minus, so the expected value of x squared is equal to 2 times 1 minus p over p squared plus 1 over p. All right, now we're ready to get the variance. Okay. So, the variance of x, remember we're talking about geometric random variable with parameter p, is equal to the expected value of x squared minus the expected value of x to b squared. Okay, so this guy we just found, it's equal to 2 times, look at that, 1 minus p over p squared plus 1 over p minus, this was 1 over p to b squared, so it's 1 over p squared. Okay, this one's compound, this is 2 minus 2 p, common denominator p squared. Here it's plus p, Here it's minus 1. Okay? And so let's see what that is. So 2 minus 1, that's 1. Minus p. That would be all of p squared. And that's what we said. Fantastic. All right. That having been done, I'd like to do a quick example, and then we'll call it quits. So as an example, suppose a card is randomly selected from a well-shuffled deck. Its suit is noted. The card is returned to the deck. And the deck is reshuffled. This process is performed. Until the first part is selected. Let X represent the number of cards selected. Then X is a geometric random variable. With parameter P equal to 1/4. Also, so I'll write these down kind of fast. 1 F of X is PMF, so let me just write it down. PMF, that's F of X. What is that? That is P, which is 1/4, times 1 minus P, which is going to be 3/4, raised to the X minus 1. And here, don't forget, X is equal to 1, 2, go forever. The second thing I want to make note of is that the expected value of X, remember that's 1 over P, which is equal to 1 over 1/4, which equals to 4. Well, yeah, on average, the number of times you won't have to do it to get a R is 4 times, because 1 out of 4 times is a R. 3, the variance of X, remember that was 1 minus P of, P squared. And so in this case, that's 3/4 over 1/4 of the B squared. And so that ends up being 12. Ladies and gentlemen, that's all I wanted to do for this video lecture. Thank you very much for your time and patience.